Okay, welcome back to Calculus. We're going to take a look at our second technique of integration in Chapter 7, coming from Section 7.2. And unlike integration by parts, that is a technique of integration that applies to a wide variety of integrands, things to integrate, this one's actually rather specialized. I want to show you how do we find an antiderivative for functions of this very special form. Power of sine times a power of cosine. The powers are not allowed to be negative. They're greater than or equal to 0, and they're also whole numbers. So no fractions, no 1/2 powers or anything like that. So that's what this first day of section 7.2 is about, is integrating powers of sine and cosine. Okay, so m and n here can be any non-negative numbers that are whole numbers. So let's get going. The way I want to do this is kind of show you some examples, and then at the end of the video lecture, we'll kind of summarize these examples. We'll cover all possible cases, and they actually kind of form a strategy for how to attack these things. Okay? So intrinsic to our work here is going to be some trigonometric identities. So I wanted to start by kind of looking at this. This trigonometric identity I call fundamental. It's called the Pythagorean identity sometimes, but it's absolutely a trig identity that you need to know. That for all real numbers x, if you add the square of the sine of x and the square of the cosine of x together, regardless of x, you always get the number 1. Right? That's because cosine comma sine are the coordinates of a point on the unit circle. And every point on the unit circle satisfies the equation. It's x coordinate squared plus its y coordinate squared is 1. All right, so that's a fundamental trig identity. Here, I've just got some variations on it. If I subtracted sine squared from both sides, I can write that thing like this. And then here in particular, I want to say, so cosine squared is 1 minus sine squared. So if you gave me any even power of cosine, right? An even number looks like 2 times some other number. Well, I can always write that even power as some power of cosine squared, namely the kth power, right? So that's where I'm getting the right-hand side of this formula over here. The cosine squared, well, that's 1 minus sine squared. So the point is that I can write any even power of cosine as some power of 1 minus sine squared. Seems like a weird thing to say here at this point, but you'll see why it's true. So stop the video and kind of digest that algebra if you like. Down here, I'm going to be kind of brief about it. I'm just saying that I could have also picked on sine. If I solved that Pythagorean identity above in the purple box for sine squared, it says that, and then therefore any even power of sine can be written as a power of 1 minus cosine squared for the same reason, because sine to the 2k is sine squared to the k. All right, so pause, digest that, and I'm just going to go. So let's look at this first example. So here, I don't necessarily have to name these things m and n, but that's what I'm looking at. I'm looking at a power of sine, namely the 10th power, sine to the 10th, times cosine cubed. Okay, so here's how I'm going to attack such an integral. The first step is going to look like it's a little bit random of an idea, but you'll see when this method starts getting clearer. So I'm going to take that cosine cubed, and I'm going to rewrite it as cosine squared times cosine to the first. A little bit of an out of the hat thing to do, but you'll see why I wanted to do that. Okay, so then what I'm going to do is rewrite, well, I've got my sine to the 10th, but I'm going to take this cosine squared, and using that Pythagorean identity that we just talked about, I'm going to write it as 1 minus sine squared. Cosine of x is still there, and I've got my dx. Okay, now I'm going to make a variable substitution. I'm going to let u equal the sine of x. Why? Because then du is cosine of x. If you want me to say a little bit about my strategy, that's why I split this cosine of x off. I split one of the cosines off cosine cubed because I knew that if I let u equal sine, then that extra cosine would be my du. So if I come back here to complete my substitution, this sine to the 10th, well, that's just u to the 10th. 1 minus sine squared is 1 minus u squared. Cosine x dx is du. So this technique has transformed my integral into a polynomial in u. Yeah, if I distribute my u to the 10th through here, I can see what polynomial I have. I have u to the 10th minus u to the 12th. Okay, I can find that antiderivative. I'm going to scroll so you can't see the first line there. The antiderivative of u to the 10th is 1/11th times u to the 11th. Likewise, the antiderivative of u to the 12th is 1/13th u to the 13th. I'm done taking my antiderivative on an indefinite integral, so I add the constant of integration. And then my last thing to do is to remember, well, what was the original variable? It was x. So everywhere I see a u here, I'm going to write the sign. So that's 1/11th sine. Remember, on trig functions, we write the exponent right there. So there's u to the 11th in terms of x. And I've got 1/13th sine to the 13th of x plus my constant. Okay, and I'm going to let you check. This little box just means I'm done with the calculation. I'll let you check that if you take the derivative of that thing, and it won't happen, you'll have to do a little bit of trigonometric substitution, I mean, with some identities, but the derivative of that thing would be our original function. I'm going to sort of zoom out just a little bit so we can see it all at the same time. I hope this doesn't make it too small. The derivative of the thing written on the last line would be sine to the 10th times cosine cubed. Okay, so I'm going to say something about this at the end in terms of strategy, but it'll be a mouthful there. So let me say that I will proceed this way in any one of these problems when the exponent on cosine is an odd number. Okay, when the exponent on cosine is an odd number, like this 3, then I'm going to split off a cosine. Yeah, because then the remaining exponent would always be even, right? When you decrease an odd number by 1, you get an even number. And like we said in the previous slide, any even power of cosine can be written as a power of 1 minus sine squared. So using that, every expression in this integrand I can replace in terms of sine, except for the one cosine that I have split off. So I'll always end up with a polynomial in my new variable, and the integration will be as easy as it was here. Okay, so that's kind of the general strategy. That's how I'll proceed if n is n. Remember, is the exponent on cosine. If the exponent on cosine is odd, then I always proceed like what we just did: split off a cosine and let u equal sine. All right, it's a lot to digest, but you can pause and think about it at your own speed. Let's look at a second example. And of course, in my second example, the exponent on cosine is not odd. Yeah, so that's a bummer. I wish it was odd. If it was odd, I would have proceeded just like before. So here, what I'm going to do is, because the exponent on the sine is odd, I'm going to split off a sine. Maybe you should stop this video and kind of think to yourself right now, like, oh, can you understand what my strategy is all about here? I'm splitting off a sine. So again, this exponent that remains on the sine is now even, right? You decrease an odd number by 1, you get an even number. So using our Pythagorean identity, that sine to the 4th, I'm going to write this as an explicit step. So since we're doing this for the first time, I can think of that as sine squared squared. Yeah. Why would I do that? Well, because sine squared is 1 minus cosine squared. So I've got 1 minus cosine squared, quantity squared, times cosine to the 6th times the sine of x dx. All right. And now you can probably guess what I'm going to do. Yeah, can you? I'm going to let u equal, what would I let u equal? Pause it, think about it. I'm going to let u equal the cosine this time. Why? Because du, well, it's not sine. I wish it were, but it's the opposite of sine, right? Du is minus sine x. All right, but that's not going to stop me. That -1 factor, I'm just going to put out in front. So I have the opposite of the integral. Well, this would be 1 minus u squared squared. Cosine to the 6th is just u to the 6th. Sine x dx is opposite of du, and I already accounted for my opposite out there. Yeah, so I put the thing out front. So I get a polynomial in u again. I have to do a little bit more algebra this time to see how to integrate it, right? I have to square out 1 minus u squared. So that's going to be 1 minus 2u squared plus u to the fourth. So it's a little bit of extra algebra to do this time. That's distributing my u to the sixth through there. That's u to the sixth minus 2u to the eighth plus u to the 10th by rules of exponents. Now, anti-differentiated its powers. So I get 1/7 u to the seventh minus 2/9 u to the ninth plus 1/11 u to the 11th. I'm done integrating, so I add my constant. What remains? I got to remember that u is equal to cosine, and I'm going to distribute that minus sign through as I go. Okay, so I'm going to write that I have minus 1/7 cosine to the seventh of x plus 2/9 cosine to the ninth of x minus 1/11 cosine to the 11th of x plus c. Okay, I'm going to zoom out just a little bit one more time. I hope it's small enough, or not too so small that it's not worth even doing this, but you can see the entire calculation. It's not short. This is a kind of a mathematical hygiene comment, but notice how I was willing to write many lines of computation on any one of which I didn't do much. So that has a lot of benefits. I don't make as many mistakes. If I do make a mistake, I've got a very detailed little breadcrumb tool, or trail rather, that I can look back and see, what line did something go wrong. All right. So this is how I would always proceed if my best case scenario is the exponent on cosine is odd. Proceed like example 1. If it's not, then I hope that the exponent on sine is odd. So I would proceed like this: split off a sine, let u equal cosine. Okay. So you can probably guess what's next. Yeah, so next, we're going to be looking at a case where neither one of the exponents on sine or cosine is odd. I'm choosing as an example sine squared, and you might think like, well, but the exponent on cosine is just completely missing. There is no cosine. Yeah, well, that exponent is 0, right? The integral of sine squared, you could write it as sine squared times cosine to the 0. So this has the same form as the integrals I'm talking about. It's just that if the exponent on cosine is 0, anything to the 0 power, excuse me, it's not 0, it's a 1. Yeah, so this has that form. So how are we going to proceed? We needed an odd exponent to proceed like we did in examples 1 and 2. I don't have one here, so I'm going to use an identity. This is an important identity. It's usually called a half angle identity. And so the sine squared is equal to 1/2 the quantity, 1 take away the cosine of 2x. All right, so I'm invoking a trig identity. The sine squared of x is 1/2 times the quantity 1 minus the cosine of 2x. It's usually called a half angle formula, maybe a double angle formula. I get them messed up, but this is the relevant identity. And why is that identity important to me here? Well, because in this form, if I pull out that 1/2, 1 minus cosine of 2x is stuff that I can integrate, right? In particular, the antiderivative of 1 is x. And well, this is technically with a substitution, but I'm just going to do it here. I hope you've done enough of these things. The antiderivative of cosine of 2x would be 1/2 the sine of 2x. Yeah, that technically speaking would be a u substitution itself, letting u equal 2x, but I'm just going to do it on the fly here. Okay, so I added a constant of integration because I'm done anti-differentiating, and if I just multiply through, I get 1/2 x minus 1/4 sine of 2x. Okay, so to integrate sine squared, I used this identity. I used the trig identity. Sorry about that. I used this trig identity, the half angle formula. Okay, I've got those identities written down here. I'm going to scroll down and show them to you. It's important to know these things. That sine squared is 1/2 1 minus cosine of 2x. Sorry, my identity has an extra parenthesis in there. Cosine squared is 1/2 1 plus cosine 2x. Okay, these things are important to know because it's how we integrate sine squared and cosine squared. You do it with those identities. Okay, so have them somewhere where you can refer to them, and then after you use them a few times, you'll just know them. Okay, so let's continue. I've got a fourth example here where this one's missing an integral sign, but I want to integrate sine squared times cosine squared. Okay, so neither exponent is odd. Let me show you how we'll proceed with such things. There are other ways. This particular integral could be handled by another identity. I mean, with trigonometric functions, there's always another way. Identities, but I'm just going to try to show you something systematic. So when both exponents are even, what I personally do is I take the cosine, and because it has an even exponent on it, I can write it as a power of 1 minus sine squared. In this case, it's just 1 minus sine squared to the first power. And then I distribute. So I've got sine squared of x minus sine to the fourth of x. Okay, and then I'm going to use a reduction formula for the powers of sine. So maybe you remember from our work in integration by parts, that reduction formula says that if you have a number n that's at least 2, that the square of sine, sorry, not the square, got that 2 stuck in my head. If you want to integrate the nth power of sine, the reduction formula is, well, it's minus 1 over n times the sine to the n minus 1 of x times cosine of x, take away, or plus the integral of n minus 1 over n times the integral of the sine of n minus 2 of x dx. So it's called a reduction formula because it lowers the exponent on sine by 2. It produces an integral in the formula, but the exponent has gone down by 2. So in particular, if I apply that reduction formula to the sine to the fourth, I'm going to get some expression minus an integral, some multiple of sine squared, okay? And then I can apply the reduction formula again. So let me illustrate how to do it here. I'm going to put a box around this because it's not part of the calculation above. Just reminding you of that reduction formula. So this equality that I'm writing right here, I'll show you with my laser pointer. I'm continuing from above. Okay, so I'm going to split that into 2 integrals. It's the integral of sine squared of x dx minus the integral of sine to the fourth dx. And then let me use some color just so you see where I'm looking. I'm going to replace the integral of sine to the fourth dx with the right-hand side of that reduction formula up there, taking n to be 4. All right, so let me keep the reduction formula in view. This integral of sine squared is just going along for the ride. Minus, put a bracket because there's going to be more than one term. And now I'm looking at the reduction formula with n equal to 4. So I've got minus 1/4 sine cubed times cosine plus n minus 1 is 3 over 4 integral of sine squared. Okay, going to distribute that minus sign. So I've got sine squared of x dx plus 1/4 sine cubed cosine minus 3/4 the integral of sine squared. And I'm going to combine those terms. Look, in this expression, let me grab some color so you see what I'm talking about. I've got an integral sine squared dx. I've got the same integral right there, but the second one has a coefficient of minus 3/4. Well, 1 of something minus 3/4 of the same thing is 1/4 of that thing. So I've got 1/4 sine squared. And then this other stuff, I've got the 1/4 sine cubed cosine squared. So now in practice, the integral that I have remaining is this integral sine squared x dx, which I would do by that half angle formula that we just talked about. we just happen to do the integral of sine squared dx, and I can almost remember the answer. Let's see if I can. So we just computed this, so I'm doing it from memory above. You could stop the video and go back and look, but I think that it was 1/2 minus 1/4 the sine of 2x. I'm nervous. I'm going to scroll back up and look to see if I'm doing that from memory correctly. I'm going to add my constant because I'm done integrating. So what I want to go back and look, I'm going to scroll up real quick here, is I want to see, did I get that right? Is the integral of sine squared of x equal to, I can already tell I've got one little typo here. It's supposed to be 1/2 x. So there's one thing I'm fixing, but I'm going to go back up and look, right? So what I'm highlighting in yellow, we just computed. Let me scroll back up past our things. Yeah, 1/2 x minus 1/4 sine 2x. Good. That's exactly what I wrote there. I've added my constant. I'm just going to clean up here, distributing my quarter. So what have I got? 1/8 x minus 1/16 sine 2x plus 1/4 sine cubed x cosine x plus c. All right. So that illustrates the case where both the exponents are even. What do? You rewrite everything in terms of power of sine, and you use the reduction formula. Okay, so I'm going to end this video by just trying to summarize what we were just doing up above. So I'm looking at integrals of the form power of sine times power of cosine. Powers are non-negative numbers that are whole numbers. So the way I like to process this, the first thing I try to look at is this number n, the exponent on cosine. I hope it's odd. So if that number is odd, an odd number has the form 2k plus 1, then I split off a cosine, leaving an even power. I rewrite that even power as a power of 1 minus sine squared, and then I make the substitution u equals sine. Turns it into a polynomial in u. If I don't get my wish, if the number n is not odd, then I look at m, and I hope it's odd. If the number n is even, then I hope m is odd. If m is odd, then I split off a sine, leaving an even exponent on sine. I can write that even power of sine as a power of 1 minus cosine squared. Then I let u equal cosine. Okay, and my du is sine x dx. Well, it's its opposite. Then I get a polynomial in u, and I integrate it. The unhappy case, the third possible case, is where both n and m are even. Okay, if they're both even, neither one of them is odd, then picking on one of them, I'm going to pick on n. I'm going to pick on n. If it's an even number, it's 2 times something. So I replace the cosine, that's the power on n, with a power of 1 minus sine squared. Okay, that'll, after I do the algebra, give me powers of sine, and I use that reduction formula, I've got it written here in a purple box, to chomp down those powers of sine, reducing them 2 at a time. Okay, so that's how you handle integrals of the forms sine to the m times cosine to the n, where n and m are non-negative whole numbers. All right, I hope this was useful. Thanks for listening.